But if you look at security vulnerabilities in the first place, what they are is just bugs. They are bugs in code, mistakes made by programmers, and they can be easily found also from the software. So looking at proactive security practices, we basically enter the domain of product security. And in product security practices, there are some basic terms that help understanding the problematics around this. So first of all, understanding the difference between vulnerabilities and threats and attacks. So whereas many security technologies focus on preventing attacks, other approaches are more interested in actually looking for the vulnerabilities, the weaknesses, the bugs themselves, and trying to fix those. And the method of doing that, how you can actually find and fix those problems, is helped by using advanced techniques like protocol modeling. So protocol modeling has changed the landscape from pure random testing and traditional fuzzing into something that is much more systematic and much more effective in actually finding those mistakes in the code. So protocol modeling basically means that you are able to model the communication sequences and the protocols in such manner that you can basically automatically generate test cases that are meaningful and extensively documented as well. So looking at fuzzing as a domain itself, it isn't really clearly defined anywhere. Many people still think that it's a process of randomly generating test cases, but quite often it's not. So there's many different techniques, there's many different processes for doing fuzzing, but the main goal in all fuzzing is to do automated security testing. And when you combine the protocol modeling techniques with anomalies, anomalies are basically what makes fuzzing tools find those mistakes. So anomalies are those slight changes in those protocol message exchanges or structures or data inside those structures in order to find problems like boundary value conditions or buffer overflows or SQL injection problems. So any type of unexpected input that the programmers were not expecting to ever come from the other communicating party, that's the anomaly aspect of the fuzzing. And then finally, in order to find those weaknesses, you need to define what type of failures are you interested in. So when you look at many of the hacker tools out there, they are only interested in exploitable problems, weaknesses which enable them to execute code on the target system. But on the other hand, if you are trying to protect your systems, or if you're trying to build secure software, you are often interested also in the crash-related problems, performance-related problems, memory leaks, and other resource-related issues in the code as well. Because those can also be used as a denial of service attack when you find a specific anomaly in a specific test case or message that reserves a slightly more memory or CPU power than a regular message exchange, then it's very easy to repeat that test case over and over again in order to drive down those critical resources in the server. And many fuzzing tools can do that easily. So for example, using our tools, you can easily run tens of thousands of sequences, messages per second. So fuzzing tools in the test generation aspect can be considered a bit similar to those load generators that are used in the quality assurance as well. So what is zero-day vulnerability management then? Basically, it's a very simple process of detecting attack vectors. What are those potential interfaces that hackers can abuse in order to get into your critical servers or services or networks? And then prioritizing those and finding the zero-day vulnerabilities, those weaknesses in those protocol interfaces or communication interfaces. And then after you have identified those, it's often immediately stepping into the defensive side. So looking at mechanisms how you can defend against those zero-day weaknesses, while the vendors are given much more time actually to provide good quality fixes and patches for the weaknesses. So instead of urging them to provide a patch in a day, you can wait for a good quality patch that doesn't put your systems at risk from its quality perspective. And on the other hand, also often you can protect your system before disclosing the weaknesses to anyone else but the vendor. So you can keep those weaknesses confidential to you and your trusted vendors. But one of the key areas in cost savings perspective is that you can do this quietly, slowly, at your own pace, and then push all the corrections and all the updates to your services and your systems in one big security push. Very similar way as software developers are doing when they develop the code. They have security gates and security pushes. You can also have similar kind of security testing before deploying the systems, but after deployment as well, by being able to actually prevent and protect from those zero-day weaknesses much more proactively. So going through all these steps one by one, let's start looking at threat analysis. And the focus here is looking at network analyzer-based threat analysis. So the main goal in threat analysis is to identify those threat interfaces, the threat surface, and then prioritize those for later testing and analysis. When we look at zero-day vulnerability management and the network analysis part of it, often what people think about when they think about network analysis, they think about tools like Nmap, which is a port scanning tool, or vulnerability scanners, or tools like Nessus, which help you mapping some of the risks in the network. But the major failing in many of those systems is that they only look at the server-side implementations. They don't look at any client-side tools. They can't detect old versions of browsers or DHCP clients or any client-side implementations. They are only looking at server-side implementations, and those often are not the most critical threat to the system. But more often nowadays, the attacks actually come towards the client-side implementations. So the solution for detecting those as well is looking at the network analysis aspect. So instead of depending on network scanners and just architecture designs which visualize or picture the imagined or the design network interfaces from the design perspective, a network analyzer is actually kind of reverse engineering the design from the real events and real happenings in the network. So in that way, what you actually will visualize is all the communication interfaces coming in and out from the system, and when you then use the same tools in drawing your trust boundaries, the trusted server farms or the backend systems, and then your intranet users and then the external users in the internet, you will automatically be able to prioritize those interfaces and threat vectors as well. And when you do network analyzer-based threat analysis, what you can then also easily do is that you can extract any of those interfaces, those threat templates for later use in the test process. So you can extract, for example, message sequences that are live and really happening in the network and load those into your test generators for later use.